This is a video to help you guys complete your lab molar volume of a gas. I'm going to use my data. Yours is definitely going to be different, but you can follow along with me and my data. Let's just kind of go through the questions because that kind of leads us up to some of the data things too. So the first question, hopefully you've done this already, just the balanced equation. So we had magnesium and hydrochloric acid. It's a single replacement. So the magnesium goes in, kicks out the hydrogen, which you have to remember is diatomic, and then it forms magnesium chloride, which the formula is MgCl2. So then I would balance this by putting a 2 here, and then I think I'm done. So the next thing, if you remember, we measured the length of the magnesium ribbon in order to get the mass. So what we need to do is we're going to convert this into meters first, and then we're going to use that equivalence that I gave you. So for me, it's 998. 0, there were that many grams in 1 meter of that. But every, yours is going to be different because I have different rolls of magnesium that have different values here. But for me, then I get 0.3762 grams of magnesium. I guess technically I'd only have 3 cigs here. So then, once you have your mass of magnesium, I guess you don't have to go up there, but we're going to calculate the moles of magnesium. So if I just take my mass that I just calculated, so there's that many grams of magnesium. I know that's kind of messy. That's a 0. You're going to have a different number than me, but we're going to do the same work. So you know how to convert to moles because you know the molar mass is going to help you. So when I do this, I convert my grams into my moles, and for me, I get 0.00155 moles of magnesium. And again, I want to keep my significant figures. I have 3. I kept 3. Remember, these leading zeros are not significant. Next question is, I'm going to take my atmospheric pressure and convert it into from inches into millimeters of mercury. So the pressure in the room for when I was collecting my data was 29.56 inches of mercury, because that's what our weather apps like on our phone and are going to be in inches, and we're going to convert this to millimeters of mercury. So I know that there's 2.54 centimeters are in an inch, and then I know that I have 10 millimeters are in a centimeter. And again, if you want to double check, the inches of mercury cancel, centimeters cancel, and we end up with millimeters. So when I do that, I get 750.8 millimeters of mercury. Now we're going to look at the vapor pressure table. And what we need to realize is that, I'm going to draw you guys a picture. Sorry, I got to get this out of the way. When we were doing that gas collection, you know, we had our beaker with the water and we have our tube in there, right? In that tube, there are hydrogen particles that create their pressure, but there's also water vapor in there because of the fact that we had water in the solution when we were doing the hydrochloric acid is dissolved in water. So some of the water gas was in there along with the hydrogen. So what we need to do is figure out what's this pressure of the water, and then we know the pressure in the atmosphere, which would have been what's in the room, that we just calculated in the previous question was 750.8 millimeters. And then that we know because of Dalton's law of partial pressure that the total pressure in the room is going to be equal, or in that tube is going to be equal to the sum of the pressures. So the pressure of the hydrogen plus the pressure of the water. So to figure out the pressure of the water, we want to look at our data table and look at our water temperature. So mine is 20.9 degrees. So I go here and I'm going to round that to 21. So I'm going to assume that my water there had a pressure of 18.6 millimeters of mercury. So because of that, then I can rearrange this equation. Well, I could sub in and rearrange it after too. Let's do it that way. So the pressure of the hydrogen is my X, and then the pressure of the water was 18.6. So then I can solve for just the pressure of the hydrogen so that we can do all of our calculations for just hydrogen. So when I take 750.8 and I subtract that 18.6, I end up with a pressure of 732.2 millimeters of mercury. That's the pressure of my hydrogen. And that is the work that what I just did on that slide is what I would put here for number 5. I would have taken my pressure in the room or my atmospheric pressure and showed, what the pressure of the water was from that table. And then I would solve for the pressure of the hydrogen. Actually, that's what goes down here. Sorry, this question was just when we used the table and we determined that the pressure, because of the temperature of the water, was 18.6. So this answer is just from the data table, the water vapor pressure table, and then that other calculation would go down here. So now we're going to do a calculation. So for this calculation, we're going to want that value that we just got. So we would put our answer from number 6, which was 732.2 millimeters of mercury. 732 point, what was it again? 2 millimeters of mercury. That was the pressure of our just the hydrogen. And then the volume of the hydrogen that I read in the tube, mine was 37.7 milliliters, but I would want to convert this into liters or not. It really doesn't matter for this one because it's not an ideal gas law. It's a combined gas law. So I guess I'll just leave mine 37.7 milliliters. The temperature of my water was 20.9 if you remember, and then you'd want to convert that to Kelvin, so that would be just wait 1 second. So this would be 293.9 Kelvin. So in the question, we're going to calculate what if we had done this experiment on Mount Everest. And the pressure on Mount Everest is 253 millimeters of mercury. The temperature is -14 Celsius. So this is a combined gas law, P1V1 over T1. N is constant, so we're going to hold the amount of gas moles constant. And then that would be set equal to P2, which would be the Mount Everest values. I'll just put ME times V of Mount Everest over T of Mount Everest. So you would have to convert this to Kelvin. So -14, so 273 essentially minus 14 is going to give you 259 Kelvin. So then we can just sub in here and solve for the volume of the gas that it would have been had we done this at that high elevation in that really cold place. All right, so when I do the math and I sub everything in, I get a volume of 96.1 milliliters. So that makes sense. The volume is about 3 times greater because the pressure is so much lower. The temperature difference isn't that big of a deal, but yeah, you would want to make sure you sub everything in to get the exact value of what that volume would be. And if you had decided to convert this into liters, it would have been 0.0377 liters, and then this answer would have been 0.0. Mine would have been. Yours will be different because you'll have different numbers, but so you could do that in liters or milliliters. Next part, we're going to do some stoichiometry to calculate the moles of hydrogen that would be produced in the experiment. So if you remember, previously we calculated the moles of magnesium. So I'm going to start with that number, and I'm going to use my balanced equation here. And you can see that I have a 1-to-1 mole ratio. Even though it's 1-to-1, I would still want you to show your work. So I would start with that 0.00155 moles of magnesium, and then I'm going to just convert that using the balanced equation, and this is my mole step of stoichiometry. So then I would have, that same number of moles of hydrogen. Now we're going to recalculate the volume of hydrogen that we did in this number 7. So it should say number 7 at SRC for 1 mole. So what we're going to do is instead of using the Mount Everest values, we're going to use SRC values. And what we're going to do now is we're going to use P1. This would really be like pressure of the hydrogen, volume of the hydrogen over the moles of the hydrogen, and the temperature of the hydrogen is going to equal the pressure at SRC, and then we're going to calculate the volume at SRC of this gas, and we are going to have 1 mole, and we're going to have the temperature at SRC. So by doing this, we're going to calculate this volume, which then would be the volume of 1 mole of a gas at SRC. And that value, we know the accepted value is 24.5 liters. That's how many liters 1 mole of a gas takes up at SRC. So once I plugged in my pressure of my hydrogen, the volume of my hydrogen, my moles of hydrogen, and my temperature of hydrogen, and then over here on the right is the SRC values for 1 mole of a gas. 760 millimeters of mercury is the SRC pressure, and 25 degrees Celsius, which is the same as 298 Kelvin. So this is my X, and I would cross multiply and solve for that volume. And when I get the volume, I'm going to get a large number, like mine is 23,760 milliliters, and I'm aiming for 24.5 liters. That's the accepted or theoretical value of the volume of 1 mole of gas at SRC. But what I need to do is take that milliliter value and convert it into liter. So then it looks much more reasonable. Your data might not be so good. Sometimes people get maybe even up to into the 30s here, and that's okay. So you're then going to do a calculation of percent error, which is equal to the theoretical or accepted value minus the experimental value that you get in the lab, divided by, again, that accepted or theoretical value times 100. Absolute value, we just give them as being positive. So I'm going to take that 24.5, what the real volume of 1 mole of a gas is at SRC, minus